Thank you so much for the introduction too. Yeah, so I am Joseph Hidrup. I'm a researcher at Endo Labs, and prior to working at Endo Labs, I've been a PhD student at the Delft University of Technology. And for the last 4 or 5 years, I've been mainly researching and working on trying to apply static analysis at dependency management problems. And my sort of major mission has always been trying to see like how we can empower developers and try to increase productivity by using static analysis to solve security and dependency related problems. So before going into the whole topic of why we would like to adopt static analysis in dependency management, I think it's a great idea to take a step back and all the way back to the 1980s to understand why we're doing software reuse in general, because the whole idea with using dependency management is to try to improve the way and make it more effective to do reuse in general. And some couple of years ago, I was trying to look into what is the actual definition of software reuse, and I happened to come across a very nice article or like a guideline from the US Department of Commerce. And in this guideline, I found quite some interesting statements on software reuse. And some of the ideas of like what should be software reuse is that it should improve productivity and it should improve the quality of what we are reusing. And here it defines that we should be reusing, well-designed, well-developed, and well-documented software improves productivity and reduces software development time, costs, and risk, right? And that improvements in the quality of software developed from well-designed, well-tested, and well-documented reusable software components. And I'll mark these special keywords because those are the ones that we are generally trying to improve on. And if you look into what actually is like an implementation of software reuse, that is that like package manager, something that we are using quite a lot these days to be able to manage and to like easily download third-party components in our software projects. And if you use some tool, like for example, like npm, you can easily like install packages through the npm install commands. And the very nice feature with doing install is that as a developer, you can very easily install any type of third-party component without thinking about any types of problems, conflicts that might happen. And that is like really the beauty here with dependency management. Another thing is that you can easily search for packages. So like if you need like a very simple like utility, be for example like a regex parser, you can very simply search for that and find different types of versions or different types of variations of that regex parser that you can easily install in your project. And then another very nice thing is that if you're working on a utility and you would like to other people to use it and be able to like easily install it in their own applications, you can use the publish command that will easily allow you to publish packages to centralized distributions. And if you then look into like what are like the key properties of dependency management, we'll find that when we're like installing a package, so for example, here I have like an installation of trying to run with cargo. Here we can see, for example, that this application is trying to download 307 dependencies. If you're using sometimes like simple packages online, it can easily lead up to like hundreds of dependencies. And what is like very interesting as well is that with like complex and large package compositions, which you can see on the left. So I have like one example with dependency accepts. Here we have, for example, as a direct dependency to 1.38. And then we have another one that is on 2.80. And we can see that the same package can easily coexist. And that makes it also like very complicated when you have multiple versions of the same package within like a package project. And then on the other hand, another property with using packages as dependencies is that you don't really need to specify on a specific version. You can instead use a version range. So for example, we have that the accepts dependency is having a tilde range on 1.35. And then we have another one on proxy address 2.03. And if you try to resolve these dependencies, for example, today, you might get 1.37. Or for example, in proxy address, there's no new release, so you get 2.05. And then when you resolve the same dependency again 3 days later, you'll find that, oh, there's suddenly like a new version. And this highlights like that they're like yeah, like very that the dependencies in general are quite temporal because of the for some projects there's a very high development pace. So those are, let's say, like the two projects at a very local level, like that you have complex large package compositions like dependency trees, and that there are temporal properties where versions can very quickly change over time. And if you look more from like a very broader perspective, looking into the centralized distribution, I think many of us has been seeing the news with some developers deleting a package having 12 lines of code that is the left package, where like lots of other dependent packages suddenly stop working and build systems being broken for thousands of developers, or that there are some abandoned packages such as event stream, where a very clever hacker managed to install a Bitcoin stealing wallet mechanism, and also the very notorious SolarWind hacks. And this is like slowly becoming like a very big like both global project a problem that there are many that are trying to look into the very fragile infrastructure, or even try to identify packages in repositories that are very easy to not so easy, but like they're basically able to find out like weaknesses where they can easily try to manipulate or trying to like install malicious code or bugs that can in the end like affect thousands of developer projects, but also enterprises as well. And as I was saying, like there are basically like sort of like these two problems with temporal properties and large dependency trees. And the way that, if you look into the state of the art, how we have been able to try to solve it. So with temporal properties, we're able to have something called version pinning or log files. With version pinning or log files, what I mean is that instead of trying to specify like a version range for a dependency, you're able to like specify the exact versions that are, let's say, like locked. And whenever you try to rebuild the same project over and over again, you end up having always the same version of dependencies. So you're not subject to having like multiple versions, because the problem with versions changing over time is that you can easily introduce a breaking change that might break the build, and that can be very annoying to solve when you try to identify what the problem might be. And when it comes to other types of problems, for example, like vulnerabilities, updates, audit, or quality problems, or even like which functions are being deprecated, etc., we rely on dependency analyzers, bots such as Dependabot or Renovate, or plugins such as Cargo Audit or npm Audit for security problems. And how does this thing in general look like? So in general, you have, for example, like the tasks that you're looking at could be vulnerabilities, quality issues, or like updates, audits. Then you try to scan the manifest of like the project and start building a dependency tree of those packages. And if you have like a package, for example, one of the bottom, then you try to look where is it, let's say, like it's like this, let's say, like package in any way reachable to the project and client. And then through the dependency tree, you can easily identify where the problem is. And the issue with this whole approach is that by being at the manifest or package level, we often end up with having a lot of like alerts in general, and some of these alerts are always not like very useful, and I will soon come to that. And also for many, like which I've also been seeing like during my research in my PhD, is that by only like alarming problems at the package level, you also lose a bit of actionability, because you're not exactly pinpointing where in the code is a problem, and that leads to a lot of frustration and a lot of time being taken away of trying to get right to the problem. And if you do like a very close revisit to like software reuse, like on the things that we found on this US Department of Commerce guideline, if you do like a quick review, you'll find that it is very time efficient, like by being able to quickly like download and reuse packages. It is quite cost effective. This is also why like a lot of development effort is being driven towards trying to reuse as much as possible. I think there are some numbers that are saying that we are probably like reusing 80% of code that's being done open source. But coming down to the other problems is that we are having a lot of problem when it comes to risks. And this is where like both at Endo Labs, but in general, like in research as well, we're trying to see how we can try to minimize that when using third-party components in general. Do we have, let's say, like this sort of like classic alert fatigue, which I was explaining earlier? I think the main problem we have here is that we need to first try to address like the quality of analyzer, because with many of the state-of-the-art dependency tools, they are relying on metadata, which is like depicted, let's say, like on the left or on the right here, like with the package and dependencies. This is where we base most of analysis. And I think as a rule one is that we should not treat metadata as source code, because declaring, let's say, like packages does not really equate to how we're using packages. And I think the first way to kind of, let's say, like address this whole problem with doing, let's say, like analysis of dependencies is that we need to move towards usage in general. And the other thing is that by having, let's say, like dependency analysis in general, we need to start moving towards trying to make code as first-class citizens in general, because what the developers work on is basically source code. And if, let's say, like I know, for example, like in a dependency, so for example, like in the example here, like with bus, if I know there is a vulnerability and I can trace that all the way back to my main application, then I know exactly like, what is like the context, what are like, the kind of tests that I need to run in order to like isolate and see whether this is a problem in general. But if we have like this view with the dependency and saying like, hey, version 1.02 is vulnerable, it doesn't really tell me much. It's just a black box, and like I need to basically dig into the source code to see whether this is a problem. And one of the ways like to make code first-class citizens, and something that we're also doing at Endo Labs, is to try to produce call graphs of packages and also of the client code in order to kind of stitch both like client code and call graphs of dependency together to basically understand how everything, let's say, like connects together, and also do reachability analysis to pinpoint problems in dependencies. And yeah, like another problem with, let's say, like trying to enable program analysis is dependencies is that it's generally really great. I mean, going to the source code level is great, but it can be pretty expensive, and it's oftentimes not scalable, because usually when we apply static analysis or program analysis in general, we try to mainly focus on the project, not really trying to, like, let's say, like go by the project and dependencies together. Because when we start increasing the analysis scope from like a project to a project plus its dependencies, it becomes way more time consuming. And in order to make this work for dependencies, we need to aim for lightweight analysis techniques in general. And you're seeing some numbers here, and like this is like an example from one of my research projects where we try to build a call graph for every single Rust project. So we had, let's say, like are almost like 36,000 packages, and we're trying to build, let's say, like for 280K releases. In reality, we're able to build around 142K call graphs. So I'm saying like 67%, but it's actually 80% because I'm not removing, let's say, like broken releases, because in package repository, you might have some, let's say, like early versions, like in the case of Rust, like back in 2014 or 2015, you might have some versions that are like malformed or not, let's say, like compatible with new versions of Cargo, for example. And what is like more important here is that we were able to build all those, let's say, like releases in 10 days. And this shows that it's like possible to like easily like create call graphs, index them, and reuse them for like program analysis purpose within reasonable time. And there are, of course, some auditors will get concerned about, like, it's basically like in some scenarios it might be like overkill to add program analysis, or there's this typical question: what about Python and JavaScript that are dynamic languages? How do you deal with them? And then there's, of course, this other issues that like there's always this problem with false negatives. If I start using call graphs and my call graphs are not let's say like sound enough, I might be able to miss important elements in the code, and that might be problematic for security, let's say like applications. And yeah, we will soon go back to those questions. But yeah, and also another thing, in order to kind of like understand all those different questions, as a researcher, I always like to start framing research questions. And I thought, like, as a very interesting thing to kind of understand, like what are like really, let's say, like the trade-offs if, like applying static analysis or not static analysis in dependencies. And I thought, like, as a very simple question to kind of get an idea of, like where to kind of set the balance between, should you aim for more precision or soundness? Should you even like skip program analysis, or should you even like use it? So the first question that I had is like, what is the difference in the number of reported dependencies between traditional meta-based approaches, that is basically currently selected of the art, versus using program analysis, such as static analysis? And I was doing this research, and if you're like interested like in this work, like I have a reference to the paper. And when I looked at the like number of direct dependencies, so in this box plot we have 3 data series. One is called Craze.io, which is the metadata based. The docs.rs are basically metadata based but validated, because some metadata, as I was mentioning earlier, is that they might be broken and not actually working. Sometimes you have declared on dependencies that actually no longer exist in a repository. So all those are basically data that has been like removed. And then you have like the Prezi one, which is the call-based dependency network. But as you can see, like in the like rendering that I put here, which shows, let's say, like the median. If you look into recent year, we can see that whether you're using, let's say, like metadata-based or even call-based approach, you see that it's in general like similar. So if they are like roughly the same, we can say that if, let's say, like you're declaring a direct dependency, you're most likely also using it. So so basically like all the 3 networks in a way are basically closely like approximating each other. And then when we move to transitive dependencies, we have like a very different story. Here we will find that if you look at the median for call-based dependency network, which is the Prezi, the green one, we see that it's reporting in general 6 transitive dependencies. Whereas for Craze.io, we find that it is reporting 17 direct dependencies. And clearly here we're seeing that they're not really approximating each other. And we find that packages are like indirectly not calling 60% of its resolved transitive dependencies. And naturally, when we have such a huge gap, you're kind of interested in who is really like correct here. Like, is basically like the metadata-based approach like more closer to reality, Or do we find that using program analysis, we are basically under approximating and missing a lot of cases related to transitive dependencies? And to like find out who is like more, let's say, like correct in that way, we started, let's say, like by doing like a manual analysis. And I looked at 34, let's say, like randomly selected cases involving both direct and transitive dependencies to see which one is more correct or not. And the first, let's say, like difference that I found was that in 3 cases, we found that there were no input statements at all. With no input statements, what I mean is that there is a declaration to the dependency, but in the source code, there's no, let's say, like import of that dependency at all. And then there were also 4 cases where the dependency was like imported, but not used at all. So what we found here is that they do have an import statement, but I was not able to find any use of, let's say, like types, or let's say, like, for example, like in, like function declarations, like, for example, like an argument type related from, let's say, like the dependency, or like the return type coming from the dependency. And likewise, also like no function calls as well. And the second difference that I found when comparing like 34 cases where there were some differences, I found one case of conditional compilation. So with conditional compilation is that you usually, in the case of Rust, you would sometimes need to provide a flag to invoke a, let's say, like a functionality that exists in a dependency. For example, like you might want to like use a specific open SSL implementation, so you would need to add that flag, and then suddenly this open SSL dependency is being used within this like CFG flag. But if you do not invoke this flag, then it's not really used in general. Another thing is that there are these like deriv macro libraries in Rust that are basically doing code generation. One of the 2 most common library series, like the SERDI library that basically creates serialization and deserialization structures for structs in Rust. And like if you start analyzing dependencies in Rust, you'll find that all of them are appearing as the same, whether it's like a runtime or code generation library. And in this case, whenever it's like a SERDI library, they should technically not completely appear in the dependency tree, because their only goal is really to do code generation, and they're not really used like in let's say, like as runtime code for like a project. I think here would also be something that I guess would be nice, like in the case of Rust, that to basically classify those libraries as slightly different from like runtime libraries. And then there's also the case of test dependencies, and I think in one case I found that it was used, let's say, like in the the section for compile dependencies, but it should have technically let's say, like been in the test dependency section. And then, which I think is the most important difference here out of the case I analyzed, was that there were non-reachable transitive dependencies. So this sounds like a little bit strange. So let me go in to explain what I mean here. So like having this example, we kind of ask ourselves, like, how many dependencies like is app version 1.1 version 1.0 using? If we use the metadata-based approach, we have app version 1.0, we have lib1 version 3.2, lib2 version 0.2, and lib3 version 1.2. Here we see that app depends on lib1, and then lib1 depends on lib2, and then lib3, lib2 depends on lib3, right? And if, for example, there would be vulnerability, and in lib3, for example, there is a security problem in the use function. In the traditional conventional way, we would say that, hey, app is using lib3, so app is vulnerable because of this function. But when we look into the call graph, we find, of course, that main calls foo calls bar, then bar calls used, and then used in lib2 is called intern, right? And we see that it's basically terminating at lib2, right? Because the function unused in lib2 is not called in any way, and this is the only call that crosses over from lib2 to lib3. This is what I mean with, let's say, like that. It's not like a let's say like unreachable transitive dependency, because there is no path from, let's say, like app all the way down to lib3, because the unused function in lib2 is not called in any way through lib1 or even internally through lib2. And this is something that we get by trying to look into call graphs in general. So yeah, this is like basically like, let's say, like the main advantage. So we can directly see that, hey, like lib3 is actually not really used as a transitive dependency here. And this is a problem that by having this package-based dependency representation, we are directly assuming that all APIs of direct dependencies are being used, and then that all APIs of transitive dependencies also being used. But this is completely false. And this is what I've been trying to push in general, like even through my research, that is super critical to always take into the account of the context, because the way that app version 1.0 is using lib1 version 3.2 might be very different from how app version 2 is using lib1. Like in app version 2, you might call the intern function, right? And intern doesn't really call anything else, right? But then because of in order to compile all the source code, we will still need to use lib2, lib3 in the dependency tree. But in general, like it's very important to understand what APIs are being used, and in general, what kind of functions are we reusing from the library, because we are not reusing the entire library, only parts of it. And because we're using some parts of lib1, that also means we're using some parts of lib2 and further on some parts of lib3. So understanding this is crucial in general. And sort of coming back to the main topic of, what are, let's say, like the trade-offs or like practical implications of trying to apply program analysis to dependencies. So we found that when I was looking at direct dependencies, that in general, we found that whether you use metadata-based or static analysis, in the case of direct dependencies, it is generally like the results are like similar or approximate each other. So if you don't have like any very specific, let's say, like application, or you're kind of looking into application that only some are looking like, am I using this dependency or not? Then you probably won't really need program analysis in general. So, and of course, like the other thing is that if you don't use that analysis, you will also have, let's say, like higher recall for both security and soundness sensitive applications. But then if you look into the cons, so for example, in my manual analysis, I was not able to, I was able to find that in some cases there were like no input statements, or like in certain cases, like you will not know, for example, if certain APIs are being utilized. And also, for example, like because I was doing static analysis, I was quickly able to eliminate dependencies that are doing, let's say, like code generation, for example, like the let's say, like serialization or deserialization packages that are used in Rust. So you would be able to like not have those being visible, let's say, like in the dependency tree, because there are in practice not actual runtime dependencies. But then when we come to transitive dependencies, I would like more strongly be for using static analysis, because by being able to capture the actual usage, we are able to really quickly reduce false positives. So if you remember, like the example I was showing before, by looking into the code paths, we could see that the last like lib3 was actually not used, right? So if you would have, let's say, like different types of security bugs, warning, etc., like in the last dependency, this would have never been, let's say, like let's say, like there would never be, let's say, like a warning alarm, because we can see in the code that it's not used, right? But if you don't see in the code, we will start, let's say, like making several alerts. So by moving to the code level, we're actually increasing the actionability. But there are, of course, like some, let's say, like problems with applying static analysis, and that is that there might be a risk for false negatives. So here we have to be, let's say, like careful when it comes to security applications, because if, for example, you're using a library that is doing a lot of dynamic function dispatch, or like doing reflection or other things, static analysis is not so strong here. And this is both like a theoretical and practical problem that is not easy to solve. And here you would, for example, like miss certain, like functional call edges. And if you're using certain libraries, then it might be, let's say, like a problem. And as I was saying, like highly dynamic libraries are challenging in general to analyze from a static analysis point of view. And when it comes like to thinking about like, precision and recall, so in the way that we also been thinking at Endo Labs is that we try to focus on covering as much language features as possible, because if you are missing some language features, it could be a way, for example, to do like in different ways to do like call mechanisms or dynamic dispatch, or like supporting, for example, like later Java versions. If you don't have support for that, you will miss important calls. We try to aim for like having as much language features as possible, and this sort of comes before having precision in general, because in general, like even if, let's say, like we might be over approximating, let's say, like in the source code, it is still much better than just relying on metadata analysis. And when it comes to like aiming for precision, like applying, for example, like points to algorithms, this can easily be like not so scalable in general. And from experience, when I've been applying call graph generators for Java, for example, like Vala, if I try to use the points to algorithm, I often end up like spending hours and hours trying to build a call graph. So it's not, let's say, like very scalable in general. And there are like these kind of general implications whenever you have to think about precision and recall, is that you have to expect that, you have a project and its dependency tree. And coming back, like circling back to like the slides earlier, you can have dependency trees consisting of 300 packages or 400 or even 10, etc. But you have to be ready that there's going to be a lot of code that you need to analyze. And the other thing is that I mean, for example, like whenever like we generally apply static analysis, we are able to make certain assumptions around the code we're analyzing. But when it comes to package repositories, those assumptions doesn't really apply, because we cannot expect that package repositories are like a homogeneous set collection of libraries. There are libraries that are, for example, they might only rely on static dispatch, or there might be libraries that are doing like lots of different Java reflection that is like super difficult to analyze. So putting a number of like precision and recall in general can be very tricky because of all these different libraries and the way that they are doing different, let's say, like calling mechanism. Yeah, this I guess the same slide, and that's it for me. And if you have, let's say, like any question or want to like reach out to me, feel free to email me at joseph@endor.ai. Thanks for listening.
Thanks, Joseph. We actually have a couple questions. So what are the biggest research challenges with making dependency management more intelligent from a static analysis viewpoint?
That's a great question. So I think currently what we are doing now, like as a, let's say, like as a research area, is that we are trying to find representations to like like link different source code entities and trying to improve on that. But I think like really the next, let's say like step is that whenever we have, for example, a reachable path, can we, let's say like in some way find out whether this reachable path actually invokes the vulnerability or not? So like now we're very good at, finding, let's say like the control flow or like from, let's say like an entity in a project and dependency, but we kind of want to go down to how can we do more data flow type analysis around it. And I think this is, let's say like the biggest challenge. But of course, like the other challenge is that how can we do this more precise algorithms, more scalable? I think that's also like a very interesting thing on like how, for example, we can, summarize like library code in a way that makes it easily to consume and easy to reason about.
Thanks, Joseph. Next question that we have is that you didn't mention so much about dynamic programming languages such as Python or JavaScript. What are the challenges with applying static analysis for those languages?
That's a great question. So yeah, indeed, I didn't talk so much about JavaScript and Python. I think I even had it like as a question that I fully didn't answer. So because with JavaScript and Python, you don't have like type information around it. And without type information, it makes it very difficult to reason in a static way what a JavaScript or Python application actually does. There are like certain ways that can be done in these cases, like when it comes to JavaScript and Python. I've commonly seen that usually like having a hybrid approach works usually well, where you try to learn, let's say like the call graph by first doing some static analysis, and then use, let's say like dynamic analysis by, for example, like running test suites, or by running, for example, like if you have like a popular npm library, you can find clients on GitHub that are using it, run the test suite for those clients, and then build a call graph. And for that, you're able to learn, let's say like the different entry points and calls of that library. But it remains like a big research challenge on how to achieve, let's say like, like both, let's say like precise, but even, let's say like complete representations of, let's say like npm or like Python packages in general.
Great. Thank you so much, Joseph. And thank you for this great presentation. This concludes the webinar. Please reach out to us if you have any further questions. Thank you so much.
Yeah, thank you.